In this video, we're going to look at a few more applications of the integral test. The question here is to find the values of p for which the series summation n equals 2 to infinity 1 divided by n times log n to the power of p is convergent. Now, for p greater than 0 and x larger or equal to 2, the corresponding function f of x is equal to 1 divided by x times log x to the power of p is positive value. That means the y values are positive. Continuous is a continuous function, and decreasing. Why is it decreasing? Because the denominator is a growing function of x. X times log x to the power of p gets larger and larger as x increases, but the numerator is just a constant 1, so the ratio will decrease as x increases. So it is a decreasing function. The function f of x is decreasing. So we have the function that f of x is positive, continuous, and decreasing on the interval 2 to infinity. So we can apply the integral test, because these are the three conditions that have to be met before we can apply the integral test: positive valued, continuous, and decreasing. So the corresponding improper integral is the integral from 2 to infinity 1 divided by x times log x to the power of p dx. Let's apply u substitution. So u sub, we let u be equal to log x. Differentiate, du is equal to 1 over x dx. Now let's change the limit. X equals 2 is a lower x limit. Plug it into u equals log x, and we get u is equal to log 2. X equals infinity is the upper x limit. Plug it into u equals log x. Well, log x is an increasing function of x, so when x goes to infinity, log x also approaches infinity. So u is equal to infinity. So we can write this, transform the integral from log 2 to infinity 1 divided by u to the p du, applying u substitution and transforming the limits. So that's to transform the integral from log 2 to infinity 1 divided by u to the p du. Integrating this, we get u to the 1 minus p divided by 1 minus p, reversing the power rule, evaluated from log 2 to infinity. This is equal to 1 divided by 1 minus p times limit as u approaches infinity, u to the 1 minus p minus log 2 to the power of 1 minus p. Now the limit as u approaches infinity of u to the power of 1 minus p will be equal to 0 if the exponent 1 minus p is less than 0, which means, of course, p greater than 1. If p is larger than 1, we're going to get, essentially, the exponent will be negative. We get something like infinity to the minus 1, which is going to go to 0, and the improper integral will converge as a result. So if p is greater than 1, the integral from log 2 to infinity 1 divided by u to the p du is equal to 1 divided by 1 minus p times 0 minus log 2 to the power of 1 minus p. This is equal to, let's rewrite this, we get log 2 to the power of 1 minus p divided by p minus 1. So what we did here was we multiplied numerator and denominator by -1 to get rid of the negative in front of the brackets. So now everything kind of looks positive. So the integral from 2 to infinity 1 over x times log x to the power of p dx. This is equal to, we transform this integral by doing u substitution and transforming the limits, is equal to log 2 to infinity 1 over u to the p du, and this improper integral converges, is equal to log 2 to the power of 1 minus p divided by p minus 1. So this converges for p greater than 1. Converges for values of p greater than 1. Then by the integral test, so we always have to state this at the end. By the integral test, summation n equals 2 to infinity, 1 divided by n times log n to the power of p also converges for p greater than 1. So p has to be greater than 1 for this series to converge. All right. Now let's look at another example. Determine if the series summation n goes from 1 to infinity e to the 1 over n divided by n squared converges or diverges by applying the integral test. So let's look at the corresponding function f of x is equal to e to the 1 over x divided by x squared. Clearly, this function is positive valued. The y values are positive. F of x is larger than 0. So positive valued. This function is also continuous for all x. I should say it's continuous for all x bigger than 0 because you can't have 0 in the denominator. So continuous. And well, we also have to prove that it's decreasing, but that's not so clear, so we're going to prove that separately. So we have the first two conditions met. It's positive valued and continuous for x greater than or equal to 1 because we're starting at n equals 1, and this function is positive valued and continuous for x greater than 0. So for x greater larger or equal to 1, definitely is positive valued and continuous. So now let's prove that this function is also decreasing. So prove that f of x is equal to e to the 1 over x divided by x squared is decreasing on the interval 1 to infinity. We need to prove that. And the best way to prove that is to compute the derivative, because we know from calculus 1, differential calculus, if the derivative is negative for certain values of x, then the function is decreasing for those values of x. So let's take the derivative by applying the quotient rule. F prime of x is equal to square the bottom, x squared gives us x to the 4. Take the bottom, x squared, times the derivative of the top. Derivative of e to the 1 over x is itself, times the derivative of 1 over x is negative 1 over x squared, minus the top, which is e to the 1 over x, times the derivative of bottom, which is 2x. If we simplify this, factorize e to the 1 over x out, minus e to the 1 over x, and x squared cancels with x squared here, so we get 1 plus 2x divided by x to the 4th. Now, clearly, f prime of x is less than 0 on the interval 1 to infinity. So let's apply the integral test because all three conditions have been satisfied. We always have to show that these three conditions, positive valued, continuous, and decreasing, have to be satisfied before we can even apply the integral test. So let's apply the integral test. All right, so here's the integral test. Let's label that. Let's give it a title. Integral test. So we have the function integral from 1 to infinity e to the 1 over x divided by x squared dx. This is an improper integral, so we take the limit as b approaches infinity. Integral from 1 to b e to the 1 over x divided by x squared dx. We're going to apply u substitution. Let u be equal to 1 over x. Take its derivative, du is equal to negative 1 over x squared dx. So we get limit as b approaches infinity minus e to the 1 over x evaluated from 1 to b. This is equal to limit as b approaches infinity minus e to the 1 over b minus minus e to the 1 over 1, which is just 1. So we get limit, this is equal to limit, as b approaches infinity, of minus e to the 1 over b, minus minus, double negative is positive, plus e. And if you take the limit as b approaches infinity, we're going to get 1 over infinity, which is 0, and e to the 0 is 1. To be technical, we need to show that. So that's going to be minus e to the power, bring the limit up into the exponent limit, b approaches infinity, 1 over b, plus e, and you get 1 over infinity is 0, so we get e to the 0 plus 1 minus e to the 0, I should say, and we get e to 0, sorry, this is plus e, so the answer is e minus e to the 0, which is 1, e minus 1. So the improper integral from 1 to infinity, e to the 1 over x, divided by x squared, this improper integral, converges. Why does it converge? Because the improper integral has a finite value, e minus 1. So for that reason, if the integral has a finite value, we say that integral converges. So this integral converges, which implies that the series, the corresponding series, summation, n equals 1 to infinity, e to the 1 over n, divided by n squared, also converges by the integral test. We always have to state that. Also converges by the integral test. All right, thanks.